Hello everyone, this is Payam. In this video I'm going to analyze the impact of a rigid impactor to a composite panel using VUMAT subroutine. I'm going to explain everything step by step, so stay tuned until the end of the video. So what is a VUMAT subroutine? VUMAT subroutine is used when you want to define a new material properties which is not in the Abaqus library, like composite materials. If you want to use a composite material in Abaqus, you can only use a 2D analysis, and you need to use the shell parts. But if you want to use the 3D analysis on a composite, you need to write UMAT or VUMAT subroutine. In the implicit analysis, you can use a UMAT subroutine, but if you wanna use an explicit analysis, like here what we are using here, because we have high velocity impact, we need to use explicit analysis, which we need a VUMAT subroutine. So first of all, let's create our impactor. It is rigid, solid, and revolution. We have fixed that line. Our impactor radius is 5 millimeters. We're just gonna delete those lines. Okay, this is our impactor. We create a reference point for our impactor. And we assign a mass to our impactor in a property module. Special inertia. Create a point mass. So our impactor mass is 28 grams. And then we create our composite panel. It is solid, deformable, extrusion. So our panel is 30 centimeters by 30 centimeters. And it is 10 millimeters thick. This is our panel. So now it is a solid part. As you see, we are using a solid part. And for the layups, we need to create some planes. I'm creating an XY plane. Okay, and I'm creating planes with distance of 1 millimeter. So we would have 10 planes. Enter the value. The direction is alright. 1 millimeter. I'm gonna copy that. Okay. So we're just creating template. Well, with that planes, we create the cells. Yeah. Use that plane. create partition. Here it says select the cell to partition, that cell and that plane, and go on just like that. Now those are our composite layers. We have 10 layers, each layer is 1 millimeter thick. And now we have to assign the material orientation. In the property module, we go to the property module, and here assign material orientation. So I assume that it's a UD, unidirectional composite material, so our layers are 0 and 90 degrees. So I'm just selecting the 0 degree layers. I'm holding the shift key. I'm selecting before that we need to create a coordinate system. So we create our coordinate system. It says choose the x-axis. This would be our x-axis, and this would be our y-axis. Okay. So now we have our coordinate system. Now again, we assign material orientation. We are choosing the 0 degree layers. Done. And from here, we choose the coordinate system that we just created, and those are 0 degree layers. And we do the same thing for 90 degree layers, which are those layers. Okay, 90 degrees. If you come here to orientation, material orientation, you can see the layer orientations of our composite panel. Then we need to create our material. So I have my material in my material library, which is the carbon fiber. So if you want to use a VUMAT subroutine, what you need to do here, first of all, you need your the density, then you need depth var, and you need user material here. So what is depth var? Depth var is the number of dependent solution variables that you wrote in your code. So this number depends on your VUMAT subroutine. In the VUMAT subroutine that I'm using, it is a VUMAT that Abaqus has provided for composite material, and I'm going through that. I will explain a little bit about the subroutine. We have 17 SDVs, or solution dependent variable, and what is that? That is the variable number controlling element deletion, and this is also based on your VUMAT subroutine. So in my subroutine, the SDV that controls the element deletion is the 5th SDV. So here I write 5, and totally I have 17 SDVs. In the user material, you just need to put all the material properties in order. So these are the material properties that I'm using for carbon fiber. You can write them down or pause the video, and what you do, you just write them in order. There are 19. You don't need the density because here you have written the density here. So one by one, in order, you just write them here, which are 19 properties. Then okay, that is done. Create a section, carbon fiber, solid homogeneous. Okay, and we assign our section. Okay. Before we go to the assembly module, in the part module we need to create shell from solid, because we cannot put a solid in the assembly. No, excuse me, not solid, rigid body. So we go to assembly, composite, impactor. Okay, create a midpoint here. And we move our impactor to that point, and we need to rotate it by 90 degrees. I think 9 here. And we move it up a little bit so we make sure that there is no initial contact between our impactor and our composite panel. Flip the direction. Okay. So you can see that there is no initial contact. We go to the mesh. We will mesh our parts. First the impactor. I think that would be fine. Let's see. Yeah, that is acceptable. Element type explicit. Okay, our composite. What I'm gonna do to mesh our part in composite, I'm just gonna use a finer mesh on the impact region. So I'll sketch that plane. You can use any method to mesh your part. I just want to use finer mesh on the impact region. So now I'm gonna create cell from the sketch, from this sketch. I'm coming here, partition cell, extrude and sweep. So it says to select the cells. We select all the cells. Done. Select one more edges. We select the edges that we just sketched. Done. And it says extrude along direction. Extrude along this direction. Yeah. Create partition. So this is our panel. Now we're gonna mesh the seats. Be sure to select all the edges. Let's see how that be. Because what is important for us is the area of the region of the impact. Okay, we need to change the mesh. I'm not using a very small size. I don't want my analysis time to be I think that's good. You can use finer meshes based on your analysis. If you want, if you use the finer meshes, you can get better results. So we assign our element type is explicit linear hex. So here we don't need any distortion control. You might need it based on your analysis, but in hourglass control we use enhanced hourglass control. And make sure that you check this yes on element deletion. If you don't check that, your elements won't get deleted even if they fail. Okay, so our meshing is done. Go to our step. We create a step. a dynamic explicit step. Continue. We need to know, let's calculate our step time. So we know that x is equal to v t. So we need t here. Our t would be x over v. So our panel is 10 millimeters thick, and we use and our velocity, we use 100 meter over second. So we're gonna calculate our step time over we normally use a little bit more than that time, because we know that impactor goes through the panel, penetrates the panel, and its velocity gets reduced. So we use double of that time. Okay. The field output, we don't need the force reactions, we don't need the contact, we don't need volume, but here we need SDVs and we need status. Like here, if you don't check that, your elements won't get deleted. And we need SDVs for the solution dependent variables that we defined in the subroutine. Use 100 intervals. Okay. We can calculate the velocity of our impactor throughout the analyzers. So for that, we just gonna create a set on the reference point. Tool set create. We say RP. We select our reference point. We go back to step. History output. We create a history output. Set RP, and we actually we can get the displacement too. Displacement and velocity in the Z direction, because this is the direction that the impactor moves. V3 and U3. Okay, we are done here. Before we go to the interaction module, we go back to part. We need to create some surfaces, the impact surfaces. So we create a surface here, impactor surface. We select all the surface from. For the composite, tool surface create, composite surface, and we use the mesh type. Continue. Here we select from all entities. We need all interior and exterior entities, and we select the impact region. As you see, all entities are selected. Done. Both sides. Okay, we go back to our interaction module. Here we create an interaction property. Contact, tangential behavior, penalty. I'm using 0.3 friction coefficient. Normal behavior, we have hard contact. Okay. Now we need to create a general contact in our first step. In step 1, general contact, explicit. Here we select the surface pairs, all with self, and impactor with composite. Those are the surfaces that we just created. Okay, and we select our property. One more thing, we need to create a rigid body. Here we create a rigid body. We select our body, done, and we select the reference point of the impactor. Okay, so we are done here. We go to the next step. we define the boundary conditions. First, we define the boundary conditions of our composite panel. Edges. Holding the shift key, and I am selecting all the edges. And using caster boundary condition, it means that it can move in any direction and it doesn't have any rotationary movement. Okay. This is the boundary condition for our panel, and for our impactor, we create displacement and rotation. We select our impactor, and our impactor can't move in any direction except the 3 direction, which is the Z direction. It is allowed just to move in that direction. Okay, and we assign velocity to it. Initial mechanical velocity. We said that our velocity is 100, but minus 100 because it's moving in that direction. We are done here, guys. Let's create our job. Carbon fiber. Continue. Now here in the general tab, we choose our subroutine. In the user subroutine file, we choose our subroutine in our directory. Okay. I'm using more CPUs, and here you need to use the table analyzers just to make sure you don't get any roundup errors. Okay, let's submit and see if we get any errors. We are okay, yeah, I think. We have rigid bodies. So it's about the boundary conditions. We go back to the load. It's about the boundary condition of our impactor. That can happen sometimes. We create our boundary condition again, displacement, rotation. Okay. We just don't check the U3 direction. We submit it again. Guys, if you find this video helpful, please don't forget to hit the like and subscribe button, please. And in the end of the video, I'm going to explain a little bit about the VUMAT subroutine, but I'm going to make another video about the VUMAT subroutine that Abaqus has provided with the name of fiber.for. Yeah, that is okay. So I'm just gonna pause the video here and come back to you guys. Welcome back, guys. Our analysis has finished, so let's check our results. As you can see, our impactor penetrates through the panel. Yeah, just like that. So here we can get the SDVs from our VUMAT subroutine code. I'm gonna explain it in a little bit. We can check the impactor's velocity, also the kinetic energy. That is the kinetic energy of our impactor. That is the velocity of our impactor. That is the displacement of the impactor. So that is pretty much done, guys. With the simulation, let's go to the VUMAT subroutine. So that is the subroutine. As I explained, it is written by the Abaqus for composite materials. So what is necessary, and you should pay attention to it, that I'm using Abaqus 2020. If you guys are using previous versions of Abaqus, you need to make sure to go check the documentation of Abaqus. Just open your documentation on Abaqus, search VUMAT here, and look for the go down and look for the user subroutine interface. The interface of your code should be exactly like what is written here. Like interface is all that part, and all that part is the top part of your subroutine code. It should be exactly like what is written here. So you're gonna copy all that and paste it into your subroutine, and here is where you write your code. User coding, here is where you write your code, and it should be exactly the same as written here. So you're gonna copy that. If you're using previous versions of Abaqus, you're gonna copy that and paste it here, this part and this part. Okay, that is so important. You might get errors. This subroutine, this VUMAT subroutine, is based on the hashing failure criteria for fiber and PAC failure criteria for fiber. So first of all, you're gonna define some you're gonna define the C matrix, what we have here. Those are the SDVs that I explained before. So our SDV1 is the damage, the tensile damage for fiber. Our, for example, SDV4 is the compressive damage for matrix. Our SDV5 is states. That is the SDV that controls the element deletion, and all the SDVs are explained here. For example, if we want to get the compressive matrix damage, you go to SDV4, and it shows us the compressive matrix damage. This is a complete subroutine written by the Abaqus, and if you come here, you can see the hashing and modify hashing and PAC criteria for fiber and for the matrix. Those are the formulas for the formulas of hashing and the PAC. So to prevent from that video to take so long, I'm just gonna make another video about that subroutine. I'm gonna explain everything that's written on subroutine. I'm gonna explain you how to write your own subroutine if you want to. and even if you want to use other criteria rather than hashing or puck, I'm gonna explain you where to write your own criteria, where you need to change. So stay tuned for the next video. That is pretty much done for this video. I hope you guys find it useful. So don't forget to hit the like and subscribe button, and see you in the next videos, guys. Goodbye for now.